Yeah, the quiz today was testing you on theorem 4.3 from the reading, which I just had up here. Also awesome. There it is. And so these guys were asking me the question, what does this mean when it says row parentheses column? If A has a 0 row or a 0 column is what it means, then determinant of A equals 0. Let's prove that. You know, we're all about proofs here, right? So let's see if we can prove that theorem. They call this theorem 4.3a. If A has a 0 row, then determinant of A is 0. Now notice I didn't write column yet. All right, so A equals, what's it look like? Well, it's some big matrix, right? And it has rows that look like this. What does it mean when it says it has a 0 row? What does that mean? You guys know what? One of the rows is all zeros. It doesn't tell me which one. I'll just pretend it's this one. I don't know how big this matrix is, guys. I'm just kind of doing a proof here without very many words. Here's my proof. Proof. Compute the determinant of A by expansion. Is that a word you guys know? Do you guys know that word? Laplace expansion is what it's called formally, I guess. If not, I'll explain it. Laplace expansion along the 0 row. Right? Because if you think about, I taught you guys how to compute determinants, but it's recursive, right? You have to go along any row or along any column, right? And then, so how does this work? Well, you would say determinant of A equals 0 times the determinant of some matrix plus 0 times the determinant of some matrix, etc. And what's that equal? 0, right? You just go right along that row. Every time you take one of these, what you're supposed to do is delete the row in the column, right? And use all the other numbers. You use a submatrix. You guys remember that? That was how we computed the determinant of a 3 by 3 or a 4 by 4. But even if it's a million by a million, 1 0 row, you're set, right? And I think it is also clear that the same proof applies to a matrix with a 0 column. And that's why they just didn't want to write very much, and so they just, right? Rather than write the same statement twice and change the word, they could have done it this way. They could have said, yeah, or column, right? They could just write it over again. That's what they did. They wrote parentheses. Got it? Other questions? Yep.
I know it doesn't matter for this one, obviously, because it was zeros, but could you also just write, instead of the determinant to account for the plus and minus signs, the C, the cofactor form? The C, well, in that case, would be 4 and then whatever row we're working with.
I guess I'm trying to understand what you're saying.
So, like, for the first entry in the determinant, it'd be 0 times C.
Right. They're called the cofactors. Yeah, you've seen that in the arguments in the book. They'll write 0 CI row I column 1 plus 0 times C row I column 2, and it would be the same thing. Yeah, those are called cofactors. Sometimes this is called cofactor expansion. Yeah, that's another way to compute or to represent what it is you do when you compute the determinants. As a matter of fact, yeah, when you look at their proofs of some of the other parts of this theorem, that's what they mean by these C's. Yeah, the cofactor matrix. So, okay. Other questions? You guys got my note that you don't have to read this whole thing? I mean, there's a lot in this section. I can tell you what we learned when I was in college. We learned all about this. The determinants of elementary matrices. Because really what you're learning when you learn about these determinants is you're learning when you apply row operations to a matrix, does the determinant change or stay the same, right? Well, unfortunately, it changes. Although it's interesting because this theorem tells you how it changes. So for example, it says here, if E results from adding one multiple of a row to another row, then the determinant of E is 1. So that's kind of cool. That's an operation we do a lot. Whenever we want to get a 0 somewhere, we do that row operation. And that won't change your determinant. But we also interchange rows sometimes. Then you have to multiply by -1. And we also multiply one row by a scalar. Then you have to multiply by k. Or like on the quiz today, we had a 2 by 2 matrix. When we multiplied the matrix by k, then we were really multiplying 2 rows by k. And that's why you had to multiply the determinant by what? Yeah, well, k squared for today's quiz because it was a 2 by 2 matrix, but yeah. So that's kind of interesting.
Can I ask why that's useful?
Yes.
Like, why would you want to know how operations change it when you could just do the determinant of the end result?
Well, I guess I'll show you, because these are the kind of exercises that we had. So let's suppose I have a 4 by 4 matrix and I want to compute the determinant, right? So for example, problem 14 from your book. This is a 2.2 homework problem. So it says, find the determinant of this matrix. Oh, by the way, sometimes you'll see this. Sometimes books will write DET for determinant, okay? So 2, 0, 3, -1. I usually like to write that determinant symbol when I'm talking about a determinant. And then I'll just write the matrix notation. But if you look in the book, do you see what's different? They don't have the word DET, but there is a slight notation change.
It's similar to the absolute value.
That's exactly it. Yeah, they use these straight bars. Okay, and that's symbolizing, oh, determinant of the matrix. But I don't like that notation because I don't think every book does that. Some books use brackets for matrices. Some books use parentheses for matrices. And I would rather write out DET so you know what I mean. Okay? Now, if you had to do this problem, how would you do it? Well, what I would do if I were given this problem is I would expand along this column. Does that make sense to you guys? So I guess the first thing I'll do is I'll say, okay, this equals, well, 0 times something plus 0 times something. And then when we get down here, it's either plus or minus -1 times the cofactor matrix. So it's going to be a 3 by 3 matrix. Do you guys know what 3 by 3 matrix is going to be? some stuff here.
2, 3, -1,
Yep.
1, 2, 2, and then 2, 1, 3.
And then 2, 1, 3. Okay. Now, one other question I have. Do I need a plus or a minus here? Well, I guess when I look at the original matrix, remember we have to kind of see where that is. We follow a checkerboard pattern, starting with plus in the upper left-hand corner. So there's a minus sign there. See that? So that means I need a negative in front of that. So I guess, oh, and maybe I should use the bars because I forgot to write determinant. I guess what I could say is this is equal to the determinant of this matrix, right? So how do we find the determinant of a 3 by 3 matrix? Well, now I'm going to use some of those theorems that, that we have. So again, we're trying to find the determinant of this matrix. 2, 3, -1, 1, 2, 2, 2, 1, 3. This equals the determinant of, watch this, I'm going to switch rows 1 and 2. Which means, what do I have to put in front of that determinant symbol? A negative sign. That's one of the theorems from this section. So, again, let me be more clear about that. I'm putting a negative sign here, I'll put that in pink, because I have switched 2 rows. And the elementary matrix, it turns out, that switches 2 rows has a determinant of -1. By the way, what elementary matrix would do that? Do you guys know? We are really applying elementary matrix, I'll call it E1, which is this. Take the identity matrix and switch the first and second row. That matrix, if you multiply on the left, will switch the first and second row. And we can check that the determinant of E1 is -1. You could check that. Do you see it? Yeah. Okay. Now the next thing is, when you apply row operation 3 to a matrix, you don't change the determinant at all. So watch what I'm going to do next. I'm going to write that this equals negative determinant of what? Of, well, what I want to do, guys, is I want to turn this into a 0. How would I do that? I guess I would do -2 times row 1 plus row 2 is the new row 2. Right? So let's work this out. Row 1 is still 1, 2, 2. What does row 2 become now? Well, 0, right? Because -2 plus 2 is 0. And then I do -2 times 2 is -4 plus 3 is -1. Is this making sense? What's this last one going to become? Good, because it's -2 times 2 is -4, and another -1 is -5. That okay, Mitchell? Yeah. Okay. Let's try and do this. Let's change this one, this 2, to a 0 also. So what's the operation I would do? -2 times row 1 plus row 3 is the new row 3. And again, this row operation doesn't change the determinant, so that's really nice. So let's see, I make this into a 0. What else do I have? I guess -4 plus 1 is -3, if I did that right. And then -4 plus 3 is -1. Does that make sense? Oh, there's more. Then take the picture. Oh, all right. All right. Because we got more to do. Okay? let's do this. Let's multiply this row here by what? Yep. Let's do negative row 2 is the new row 2. Negative 1 row 2. Well, when you multiply a matrix by a constant, you multiply the determinant by the constant. That's another one of the theorems. So the theorem is important because it shows how all three row operations behave, okay? So this equals now positive, because it was negative determinant of what matrix? Well, 1, 2, 2, 0, 1, 5, 0, negative 3, negative 1. And now I have one more step. I'm going to change this to a 0 by doing what? 3R2 plus R3 is the new R3. That will not change the determinant. And so this equals the determinant of 1, 2, 2, 0, 1, 5. Now that last row changes. Let's see what it becomes. Well, the 0 stays, because 0 plus 0 is still 0. The negative 3 becomes a 0, because when I do 3 plus negative 3, I get 0. And how about the last one here? 14. Okay? So, Mitchell, do you know what the determinant of this matrix is? My hint, expand along the bottom row. It's 0 plus 0 plus 14 times the determinant of what? 1, 2, 0, 1, right? It would just be this upper corner at that point. Does that make sense? Mm-hmm. And what's the determinant of that 2 by 2 matrix? Yeah. So the answer? 14. I
see.
So, why do we care about all these properties of determinants? Because, for one reason, it really can speed up how we compute determinants, right? Because remember that, like imagine you went along this last column. Think how long that would take. Negative 1 times the determinant of that 3 by 3, 2 times the determinant of another 3 by 3. It's a really awful definition, right? But using some brains and some properties, we can get there, even on paper without a computer.
That's all some of the ones from last week's homework.
We're taking. But there, you didn't have to do determinants last week, right? Oh, but you did have to do determinants because the characteristic polynomial, right? Determinant of a minus lambda I. And so you're like, how the heck do I compute this thing? And it's a huge polynomial with lots of algebra. Yeah, that's kind of fun. So it is what it is. Another place that determinants are used, actually, there's a lot of good stuff in here. I did not say to read this far, a brief history of determinants. One thing that's really kind of cool to know is that determinants were invented before matrices. So people were multiplying together these really cool combinations of coefficients of polynomials. And then later they figured out, oh, it's a lot easier if we just write this thing as a matrix. So in the 1800s, we started using matrix notation. Yeah, Jacobians. Maybe you've studied that in Calc 3. I don't know. I'll be teaching that soon for my class. But the other place that you may or may not come across determinants is, now here's the thing called the adjoint, Cramer's rule. So Cramer's rule is a way of solving systems of equations that's, actually, I've seen this taught in high school books sometimes. It turns out that Yeah, so I've seen this in high school books. They said, okay, compute all these determinants, and then your solutions you can get by one determinant over another. But I will tell you, nobody does this in the real, what do I mean the real world? Well, if your matrix is any bigger than 5 by 5, forget it. It'll take too long to compute it. And your matrix will be bigger than 5 by 5, okay? So, but that being said, like I said, Kramer's rule is taught, and I've seen differential equations books that use this a lot because you're studying second and third order equations, and so your matrices are like dimension 2 or 3, and this is something that I guess what I want you guys to know is that if you ever need to learn it, it's here in your book. Okay? But it's not something I want to spend a whole lot of time on. So any other questions on determinants? All right. I'm putting us on break early. Let me work